Okay, so let's do a little example here. What we have is air in a piston cylinder device. Seen a lot of these so far. So we have air in a piston cylinder device, which starts off at a certain volume, V1. V1 is 0.4 cubic meters. So initially we start off at state 1. So this is state 1, and we are at some volume V1. Temperature 1, V1, and presumably a pressure P1, and this is air. This is our system. Our system is the air and the piston cylinder device. So we start off with a certain volume V1, 0.4 cubic meters, a pressure P1 of 100 kPa, 1 bar, and then we have a temperature T1 of 80 degrees C. So we got temperature, volume, and pressure of the system. That's good. And then we undergo isothermal compression. Isothermal. Isothermal means constant temperature. Isothermal compression to state 2. So we compress the gas down, and we end up at a volume V2 of 0.1 cubic meters. So we go from 0.4 to 0.1 cubic meters. So here is state 2. And now we've squeezed down the piston. So here I have our gas, and I have a volume V2, and a temperature T2, all sorts of stuff, okay? Now, during the process, maybe the system is doing some work. Maybe some energy is being transferred out of the system in the form of work. We shall see. So I'm going to put a work 1 to 2 indicating an outflow of work. We shall see if there is an outflow of work. Maybe there's an inflow of work. After all, we're having to do work on the gas to squeeze it down. We'll have to see. So once we squeeze the gas down for an isothermal compression process, then we have an isochoric cooling process. We transfer heat out of the gas, we cool it down, and we do it isochorically. What does isochoric mean? Constant volume. So then heat is being transferred out of the system, let's say, and it's an isochoric process, so the piston doesn't move. Here's our gas, and we end up with a final temperature T3, final volume V3, et cetera, okay? Okay, what are we supposed to find here? We're supposed to find the pressure at state 2 after we do the isothermal compression. And we're also supposed to find the boundary work. The boundary work as we move from state 1 to state 2 and to state 3. We're supposed to find the total boundary work as we go from state 1 to state 2 to state 3, okay? Along the path 1 to 2 to 3. Okay, so that's the plan for today. Assumptions here. I'm going to assume ideal gas behavior is valid. We're going to check this when we're done to make sure that our reduced temperature is always greater than 2 and our reduced pressure is always less than 0.2 during the process. So we'll check that IGB is valid because we're going to be using it to calculate some properties here. I'm also going to assume that the only work being done is boundary work. I could put some wires in here. We'll talk a little bit more about the various kinds of work on the next lecture. But I could put some wires in here and a resistor and pass some current through there, and I could dissipate. I could do work by passing a current through a wire. I could do something like that. Or I could put a little propeller in here, put a little propeller that spins around, and that would be doing work on the system. We'll talk about that a little bit later. Suffice to say, for right now, we're going to focus on calculating the boundary work associated with this process. Okay, boundary work done by the gas. Okay, so how are we going to do this? First of all, I am going to put up a PV diagram to keep track of how things are going. I'm going to put up a PV diagram to kind of keep track of how things are going. Always a good idea to create a diagram for what you're doing. Whoops. Okay? So analysis. And the first thing I'm going to put down is my PV diagram. PV diagram, okay? So initially I have state one, and state one has a pressure and a volume. So here is V1, and here's P1. So this is state one, all right? And I have some pressures and a volume, and I have temperature too, all right? Okay, let's get moving here. Let's calculate pressure at state two. So how do I get pressure at state two? Well, note that the process 1 to 2 is isothermal compression. Process 1 to 2 is isothermal compression. In other words, T is constant. T is constant. Isothermal means constant or same temperature. Okay, that's good. Now, how can that help me? So the next question to ask is, what quantities or equations involve pressure that maybe we can use? And remember, the ideal gas law is valid. Ideal gas law has pressure in it. Ideal gas law has pressure in it. Let me write the ideal gas law here. So let's see. PV is equal to mRT. Now, let me solve this for temperature. Temperature equals PV over mR. Okay? Now, the process is isothermal. That means T1 is equal to T2. So note, T1 equal to T2 because process 1 to 2 is isothermal. Okay, well, let me take this equation and evaluate it at state 1 and state 2 and set them equal to each other. PV over mR evaluated at state 1 is equal to T1. So I'm just evaluating the ideal gas equation solved for T at state 1. But this is also, T1 is also equal to T2, which is PV over mR evaluated at state 2. Okay? So this means PV1 over mR is equal to PV2 over mR. P1 V1 over mR, P2 V2 over mR. The mRs cancel, and we end up with P1 V1 is equal to P2 V2. So let me solve this for P2. I'm losing chalk here. Pressure at state 2 is equal to pressure at state 1 times V1 over V2. Now, let's see what we know here. I know pressure P1, I know V1, and I know V2. V1 is 4 times V2. 0.4 versus 0.1 cubic meters. So let's plug in. P1 is 100 kPa. V1 is 0.4 cubic meters. And P2 is 0.1 cubic meters. The cubic meters cancel out and the units become kilopascals. And so this is 4, and I get 400 kPa. P2 is 400 kPa. P2 is 400 kPa. Okay? So P1, 100 kPa. So we have an isothermal compression process. As you squeeze the gas, the pressure goes up and the volume goes down. We start off at 0.4 cubic meters, and then we end up at V2, which is 0.1 cubic meters. But the pressure goes up to P2 is 400 kPa. So this is state 2. So the isothermal compression process looks like that on the PV diagram, up and to the left. It's not a straight line, it'll have a curve to it. So don't make it quite straight. Have a little arc to it. Convex, got a bit of convexity to it. Okay, so that's P2. That's P2. What else are we supposed to find? What else are we supposed to find? We're supposed to find the work from state 1 to state 2 and then to state 3. So find the total work. Find the total work. Well, how do we do that? Work 1 to 2 to 3. Oh, maybe we should finish the PV diagram before we go on to the work. Once we get to state 2, it says that we have isophoric compression to a temperature 1/2 of T2. So we have some sort of a cooling process going on, okay? Now, as you cool it, the pressure is going to fall. Fine. Pressure is going to fall. So the path from state 2 to state 3 is going to look something like this. Isophoric process, state 2 to state 3. Okay, I don't know what the pressure at state 3 is. I'm not asked for it. But that's basically what the process looks like, okay? Of course, the work is the entire area under the curve. So the boundary work from 1 to 2 to 3 is given by the area under the curve, all right? This is not a straight line here, so you cannot estimate the area under the curve using some sort of geometry, all right? We have to calculate the boundary work over the process. Okay, so what is the work from state 1 to state 2 and then to state 3? Well, that's equal to the sum of two works. It's the work from 1 to 2 plus the work from 2 to 3. It's a two-part process, 1 to 2, 2 to 3. Two-part process, so we got to calculate both works, okay? Let's do the hard one first. Let's calculate work from 1 to 2. Let's do that. Let's calculate work from 1 to 2. Let's see here. Work 1 to 2, and this is actually boundary work. What I mean by that is boundary work. That's going to be the integral of PdV from the initial volume V1 to the final volume V2, okay? Now, I need to get pressure as a function of volume somehow. What is pressure? Well, Note that the ideal gas law is valid. PV is equal to MRT, okay? And that means pressure is equal to mass times the gas constant, R, times T divided by the volume. P equals MRT over V. All right? Now, I could substitute that into this integral here. The only little thing is, I know what temperature is. How do I know what temperature is over the process 1 to 2? It's an isothermal process, and I get temperature of 80 degrees C over here. So here's temperature T1, just convert that into Kelvin, and I could immediately plug it into the ideal gas law. So I do know the temperature. The gas constant, I could get it. I could get the gas constant if I wanted, fine. But I don't know the mass. I could calculate it. I could calculate the mass. I could. I know pressure, temperature, and volume at state 1. So I could use the ideal gas law to crank out the mass. I could do that. But I'll tell you what, I'm being a little bit lazy about that. I'm being a little bit lazy. I don't want to calculate MR. The MR term, I'm not interested. I don't want to calculate MRT. I don't want to calculate the MRT. So what I'm going to do is the following. I'm going to take advantage of the fact that this is an isothermal process. That means that this quantity here, this guy is a constant because it is isothermal. That whole term is a constant. That means pressure times volume is a constant. So this guy here is equal to a constant, and guess what that constant is equal to? The pressure times the volume anywhere along the path 1 to 2. I'm going to evaluate pressure times volume at state 1. I'm going to evaluate that at state 1, and that's equal to MRT. So I'm going to substitute P1 V1 into MRT. Because it's an isothermal process, MRT is constant. What is MRT actually equal to? It's equal to pressure times volume anywhere along the path 1 to 2. I do know pressure and volume at state 1. That's on the path. I know pressure and volume at state 1. I'm going to use what I know and a little bit of algebra instead of cranking out the mass. I don't need the mass. So this is going to give me pressure is equal to P1 V1, and then I have 1 over volume. Okay, so that's pressure from state 1 to state 2 along the path. Okay, let me make the substitution here then. Integral P1 V1 over volume, d volume, and that goes from V1 to V2. P1 and V1 are constants, so I can pull them out of the integral. And I get P1 V1 integral dV over V. And again, that's from V1 to V2. P1, V1 are constant. P1, V1 are constant, so I can pull them out of the integral. All right. Now, what's the antiderivative of 1 over V? It's a natural log of V, so I can immediately evaluate this integral. So I get P1 V1 natural log, and I have V2 over V1. P1 V1 natural log V2 over V1. I know everything. I know these volumes, and I know pressure P1. Let's see here. The pressure was 100 kPa at state 1. The volume was 0.4. So I have 100 kPa, 0.4 cubic meters, and then I got the natural log of V2 over V1. V2 was 0.1 cubic meters, and V1 was 0.4 cubic meters. The cubic meters cancels out in the natural log. It better be dimensionless in there. Okay? Let's see, what's my work? What is my work here? By the way, this natural log is going to end up being negative 0.1 over 0.4, so it's going to be negative, and I get negative 55.45. Now, what's my unit there? Negative 55.45. What is my unit? Well, I've got a kilopascal and a cubic meter. kPa cubic meter. I'm starting to run out of space here. Tell you what, I'm going to go right over here. So I have negative 55.45 kilopascal cubic meter. Well, a pascal is a Newton per meter squared. The meter squared partially cancels out with the meter cubed, leaving 1 meter over, and I get Newton times a meter, which is a joule. So this is equal to negative 55.45 kilojoules. Work boundary. Work done by the system. Boundary work done by the system is negative 55.45 kilojoules. Box it up. Now, what does this negative sign mean? What does this negative sign mean? That means instead of the system doing work, work is being done on the system. Well, that makes sense. We're actually squeezing the system down. We're having to apply a force. We're having to apply a force at the top of the piston and push it down. So we're actually doing work. We're adding energy to the system in the form of work. That's what the negative sign is for. Note, W bound greater than 0, system does work. W bound less than 0, i.e. negative, work done on system. System does work, or work done by the system. System does work, work done on the system for when boundary work is negative. Okay? So I'm going to squeeze it down, and the work from state 1 to state 2 is 55.45 kilojoules on the system. That's what the negative sign is for. Okay? And we did that by actually evaluating the interval. Work is the integral of PDV. Okay? Now let's calculate the work for process 2 to 3. Work process 2 to 3. Work 2 to 3. Let's write the integral. It's equal to the pressure times dV from V2 to V3. Okay? Now, one thing to notice about the process 2 to 3, it's constant volume. It is isoporic. If volume doesn't change, then there's no area under the curve, and this integral is 0. 0. Why? Because it is isochoric. In other words, volume is constant. Volume is constant. Isochoric. No work from state 1, from state 2 to state 3. Okay. Work 1 to 2 to 3 is equal to boundary work is equal to boundary work from state 1 to state 2 plus boundary work from state 2 to state 3. We just found out that was 0. And we get negative 55.45 kilojoules. So boundary work 1 to 2 to 3 is negative 55.45 kilojoules. Negative 55.45 kilojoules. Box it up. All right? Okay, so we use the ideal gas law to calculate the boundary work from state 1 to state 2. I think we better make sure that the ideal gas law or ideal gas behavior is valid. If you look over here, it's one of our assumptions, IGB valid. Maybe we should check it. Let's check that IGB is valid. Let's see here. First of all, let's check the reduced pressure. Remember, for the ideal gas law to be valid, so let's see here. IGB, ideal gas behavior, valid if P reduced is less than 0.2 and T reduced is greater than 2, okay? You're safe. Z is approximately equal to 1, and your answers are going to be good to within 1% or 2 if these are the case. Let's find the maximum reduced pressure. Let's find the maximum P reduced maximum in our process. Let's find the maximum reduced pressure. And if it is below 0.2, we're good to go everywhere. Okay, let's find the maximum reduced pressure. Let's see here. Where might the max reduced pressure be? State 1 to 2, and then we get cooling. As you cool the gas, the pressure should fall, done isochorically. So a gas in a rigid container, you cool it, the pressure should fall. The maximum pressure should be at state 2. Maximum pressure should be at state 2. So that's going to be equal to P2 over P crit. P2 over the critical pressure. What is P2 over the critical pressure? Let's whoops. Sorry, give me a second. We need the critical pressure. We got the pressure at state 2, but we don't have the critical pressure. So let's go to the text here. And let's find the critical temperature and pressure for air. Oops. So table B1. Air equivalent. It's a mixture of nitrogen and oxygen primarily. Molecular weight, critical temperature and critical pressure, 37.7 bar. P2, 37.7 bar. P2 is 100 kPa. And P crit was 37 bar. By the way, there's 1 bar per 100 kPa. So that cancels out. And I get 1 over 37. Bars cancel out. Oh, 1 over 37, what's that? Pretty small. Where's my calculator? 1 divided by 37. 0.02. 0.02. So P reduced max is equal to 0.02, which is definitely less than 0.2. Put a check there. First check on the validity of ideal gas over our process. Looks good. Let's calculate the minimum reduced temperature. Remember, T reduced has to be above 2. So let's calculate the minimum T reduced minimum. Reduced temperature minimum. That's going to be, well, temperatures here. Temperature T1 is 80 degrees C. Then we have isothermal compression. So T2 is equal to T1, which is 80 degrees C. How do I know that? Because it is isothermal compression from state 1 to state 2. Okay, so T1 is equal to T2. And then I know that T3 is a cooling process where T3 is equal to T2 over 2. All right? So temperature falls by 50%. By 50%. I'm going to interpret that as a 50% drop in centigrade. I think that's how I'm going to interpret it. So 40 degrees C. I think that's how I'm going to interpret that in centigrade. Okay? In centigrade. Well, let's see. We'll see in a minute. Maybe both will work. I don't know. Let's see here. So T3, the minimum temperature in the process is therefore T3. So that's T3 over T crit. Let's see here. T3 is 273 plus 40 degrees C. And that gives me degrees in Kelvin. The critical temperature, what was that, 133 degrees Kelvin for air? We'll see. Air, 133 degrees Kelvin. 133 degrees Kelvin. Kelvins cancel. 273 plus 40. So we have 313 divided by 133, and I get 2.3. 2.35. T reduced min equals 2.35, which is greater than 2. IGB is valid. If I interpret T3 as half of T2 and I interpret that in absolute instead of centigrade, so what? I get 273 plus 80. 273 plus 80, what? 353 divided by 2. 176. 176 divided by 1.33 is not greater than 2. So I'm going to interpret this as T3 is half of T2 when I'm measuring it in centigrade. Okay, that's how I'm going to interpret it. In any event, reduced temperature and pressure criteria are met, and the ideal gas law is valid. All right, ladies and gentlemen, we will finish our discussion of work next time. We'll talk a little bit about other forms of work, and then we'll move on to a second path function called heat. Heat is a non-mechanical transfer of energy. And it's treated just like work. It's a path function. So we'll talk about heat and what we can do with heat. Take care, ladies and gentlemen.